put some force on the top. One that's connected to something that has an L. There's a moment at the bottom. There's a D. And there's a pushies and pulleys thing going on. P stands for pushies and pulleys. You can call it tension and compression if you want, but for this purpose we're going to call it pushies and pulleys. That's 80% of structural engineering. I'm not really a joke, but we're going to beat the heck out of this a little bit. The relationship here is always true. Force times length equals a moment, which happens to equal the pushies and pulleys times the distance d. Force times the length equals moment, which also happens to equal pushies and pulleys times the d's. I'm just going to belabor it. If you have that relationship down, it'll scale through all building structures. These are real barn burner questions. If the F goes up this relationship, length stays the same, D stays the same. What happens to the P? The P's go up. If the L happens to go down, everything else stays the same. What happens to the P? P goes down. Go for the gold. The D goes up. Everything stays the same. What happens to the P? The P goes down. Sounds very simple, but it really is. Belaboring this point a little bit more. These relationships hold true through all kinds of things. I'm going to take a big conceptual leap here. So just try to stay with me. It's supposed to be a joke. that stays the same. That a cantilever, it's going up that way, doesn't matter, thing stays the same. Stays the same. Stays the same, you can make it small, you can move it to the left, doesn't really matter. The thing's always true. Important thing to note, if you take one of these cantilevers and you stick another cantilever on the back side of it, well, now you have a beam. If you have that relationship down in your head, you stick another one on the back side, well, you've got a beam. That's the analysis method. It's very simple to remember. You could even go for the gold and kind of daisy chain a bunch of these cantilevers together. And what have you got? A moment frame. You can use programs to beat the heck out of it. You can different methods to solve it. Doesn't really matter. You get the idea of a frame just by connecting cantilevers. I'm going to just do it one last time and won't go back to it. Now, there's going to be an introduction at some point here. I'm just trying to launch into this because if you can remember this, you're clear sailing. There are engineers that I've met who can't keep that in their mind. They're almost useless. There are people that keep it in their mind and they're great. The best example that I've ever seen a person keep it in their mind, and somebody I always think of when I think of engineering, is good friend Michael Jackson. So I'm going to take the presentation, kind of throw it into a hole here. I mean, he's the man. This much we know. Something in this concert which is worthy of note. I'm just going to skip a couple minutes to it. It's all gets kind of summed up in an MJ. How does he do it? Some people must know. Bear with me. We don't need to wonder because we now know the ASCE analysis method, which actually isn't Latin, it reveals it's smooth criminal analysis method. So what do? You take your T, try to form where that T is. For our purposes, we'll just make it easy and show where he's leaning. Find your force. We'll just pretend it's him throwing himself forward. That's happening over some length, somewhere near the middle of his body, doesn't really matter. There's a moment happening at the bottom, whatever. Distance D, it's called a foot because it's the length of his foot. And there's pushes and pulleys happening at the bottom. That sums up how this is happening. You can run through this, you can imagine a force, imagine the length, and get your moment at the bottom. His foot is a foot. You can get the component, the pushies where he's pushing on his toes, and the pulleys that's presumably keeping his heels back. How does he keep his heels back? Michael Jackson is a patent owner. He patented the method and means for creating an anti-gravity illusion. These kind of foo-foo dance shoes that it looks like they're wearing are actually big glorified moon boots. They come up to here because, and they've got a V-shaped thing about in the heel. Because at a certain time when you're being distracted by the bomb or whatever, pegs come up on the stage. So he hooks in and leans way over, which is basically all the structure does. Wherever you need a pushing and pulling, you pull. In this case, it's the pegs. If you had your cameras out and you were dying to remember this fun fact, you can take a picture of this and remember you do. There are other ones that are more notable that I recommend remembering somehow, however you do it. But yeah, if you could keep your head around the anti-gravity lean, the smooth criminal method, you can scale this up to skyscrapers. Oh yeah. Can't let it go, right? It's another video of Michael Jackson. It's short. On one side of your mind, you want to think, whenever you see a structure, think of MJ. But for this example, when you see MJ, think of a building blowing in the wind and try to feel how that is. The same pushy and pulley is what you have to do as a structural engineer. Where do you need the pushies and where do you need the pulleys? I kind of barreled through that just to plant the seed, and we'll do a quick introduction. My name is Mike Barron. I'm originally from LA, New York. Went to RPI, Civil Engineering, Structures Focus. Graduated in 2006. Tufts University, got a master's in structures, just doubled down on it. There, worked with 3 structural firms in Boston. A big, a medium, a small, best way to think about it. And I now work at the Chazen company as one of the structural engineers down here on River Street, so I don't live very far. I'm licensed in New York, Massachusetts to design structures. I worked at a bunch of structures. Building in Syracuse University, MIT Cancer Center, new building that went up, Children's Hospital of Philadelphia, just the first 12 stories of it. It's eventually going to go to 23. Just big braces and big plate girders, like a ton of steel per foot. Liquid money put in steel. Structural engineering, you work on facades. Because the problem with facades is they're full of stones. Stones are heavy, they eventually fall off. Who the hell's ever going to know that there's this cracked stone up here until it falls off and almost hits a baby carriage? True story. One of the reasons why some more larger cities have laws. Somebody's got to dangle off the side of the building and at least look at the facade, see if there's a crack. I wasn't the guy in the road. I was the goon on the ground. I've went in swing stages looking for cracks, though. Structural engineering can be fun. Office building, deteriorated concrete is a great field. The whole world is built upon reinforced concrete. Steel is a glorified battery, bagging the rust. So if you go into concrete repair, you always have a job. There's a professor now at RPI that just has a focus on concrete repair. And there's something also called the International Concrete Repair Institute, upstate New York chapter, which are going to be meeting for pretty soon. We're just going to talk about this. You go into facades and building envelope. Envelopes keep the rain out, keep the heat in or out, depending. You go digging and looking for trouble. The structural engineer will crawl under buildings, but Smaller building, big building, doesn't matter. It's Michael Jackson. Even worked on a guy wanted to live in a concrete half donut. Yeah, sure, we'll sign that for you. And it smelled like concrete. Doesn't matter. There's a whole bunch of stuff you can do with it. But it's me in a nutshell. What comes next? Oh, as a structural engineer. Just to put a bow around the whole thing, I'd offer there's two ways to view the world. People fall into these kind of two general categories. You think the world is simple. You think the world is complicated. Either one is wrong. But I'd offer that an engineer thinks the world is just full of simple things. Gravity goes down, the wind blows, raindrops, whatever. Just simple things. But there's so many happening at the same time, it'd be hard to keep track of. So what's your gig as a structural engineer? Over time, you develop a mental framework to break everything up and just be able to identify the simple things. Your Michael Jackson, your wind loads, whatever. And then find some way to keep track of them all. This is the real pain in the ass part. You'll spend months trying to keep track of all the loads that come through a building, even though you'll figure out how to design the building the first week. But it's these two things. This is the thing you're here at RPI to do. Don't worry about the advanced analysis methods that comes later. Just don't leave without being able to identify the simple things. Because you'd almost be worthless coming to the design office if you can't say, well, I don't know how the building works. I don't know how a beam carries a bending moment. I can do all kinds of computer analysis programs. It doesn't sound good on the first day. I know, because I don't know how to do very elementary, simple things. Is anything Michael Jackson? So the one we're going to just beat the hell out of is this simple thing over and over. But we can do it actually in a more practical way. Talk about a retaining wall. Nice little model, friendly students. Anybody who's taken foundation design, soil mechanics, knows that the soil is like a big pile of Cheerios. It wants to fall over. And if you're going to resist that motion, you've got to push against it, but the wall's going to push back. You can spend a class just figuring out what the magnitude of this force is. If you're just taking soils, well. But at the end of the day, it's just another force. And you form your little Michael Jackson figure. If you want to know how this wall isn't falling over, well, length, D, pushes and pulleys, you know that this wall is pushing on this end and keeping its back part from pulling up somehow. By using that, you can use reinforced concrete design, and then again, get it right down to the exact number, but you can get it pretty close in about 5 seconds by using this, which sometimes is all you need to do. How do you use the pulleys? Jackson. And steel is just a glorified rubber band. You want tension? Well, where do you want to put the rubber band? You put steel wherever you want the tension force to be. You don't necessarily just put steel because that's what people do, which you'll be surprised what comes through an office. People just, well, you put number 4s at 12. That's what you do. You put number 4s at 12 right up to the point that you don't. Indication. You put steel wherever you want tension. Otherwise, it starts to crumble and fall over. You walk around the neighborhood, you just see these all over the place. You people put up blocks, that'll keep the soil back. A nice humble garage. People, it's a garage. Nothing horribly complicated about it, but these things fall over. These people screw up this little thing here. They just build it and wonder why the thing, pretend this is a cereal box and cut off one side of it. It just kind of falls in on itself. But not us, we're structural engineers. The wind will blow on the side of the building. So it's wind will be pushing up on the roof. How does it get resisted? Whatever's touching the ground must be the thing. You make your T's, you figure out what your force is, whatever it is. It's got a length, it's got a D, pushes and pulleys. Jackson. I'm just going to keep reading. But again, it's another thing. Michael Jackson has pegs in the stage to keep him from falling over. You have to have the same kind of pegs in this little wooden thing with that. He'll people, or strong kettle cellulose, all these kinds of products, but wherever you need a tension force, you stick a peg. Tension force is up there, otherwise that'll pull it apart. Wind blows this way, he's going to tension. Wind comes the other way, he's going to tension. A lot of people will build these things and wonder why the building falls over. They forgot the tension. That's how they look like when they're installed. Come up with the concept early, then you can figure out the forces later. Here's an example of a 3-story shear wall. If you notice, you've got something to carry tension over here. You don't have anything over here. There's no straps in here. It's an example of what happens when you don't keep pushes and pulleys in mind. There's only 3 types of forces. It doesn't matter if the wind's pushing on this thing or you're shaking the base and having it accelerate. You both put forces into one. So this is a shake test. Sides are doing fine. Sides really aren't. If there's actual weight on the building, it will fall over. And at the end of the day, nobody will care if you've done calculations and you've analyzed it for a long time. The whole gig is you say to a building, trust me, it works. If it works, great. Take your feet home when you pat yourself on the back. If it doesn't, there's nobody else. That's the gig. Steel frame building, it's the same idea. Wind will push on the side of this building, breaking into 2 forces. That's got to find some way to the ground. These cables and whatnot really they act like the T's. Put a force on the top, put a length on it, put a D, pushes and pulleys. In this case, equal and opposite, these cancel out. Equal and opposite force at the same time. Just a glorified tug of war. They cancel each other out. Nothing happens there. Great. And we can see is if you had one brace frame here, you had your pushes and pulleys here, two braces next to it, you're almost forming one really long B happening here. So just by manipulating these relationships, you can frame out a building real quick. Another steel frame building, same damn thing. You see these complicated brace frames, but really all you're asking you to do is to cantilever up from the ground to keep the thing from swaying over in the wind. And you could do the letters in one. It's a building in Albany, 677 Broadway. When the wind blows over, when the wind blows, it's the same thing. There's a brace frame in the middle. Each of these brace frames, you'll spend a lot of time tracking the forces, and there'll be a force coming in, and you'll have to make sure all this is right. But right off the bat, surprise, surprise. That was all just laying kind of the groundwork, just beating that all to death. Because the fun comes when you can see how those simple ideas are at play, something other than the wood shear wall. So we're going to talk about 2 builders. 2 designers. Are there any architects in the room by any chance? That's fine. There's this ongoing feud or discussion that architects and structural engineers, they're at loggerheads. Get it out of your head. Your architects are going to be your best friends. Because you can't design a cool structure without an architect kind of leading the way and getting the commission. But an architect can't make his crazy thing stand without you. You can be the best structural engineer in the world, and you can be designing the best gazebos in your backyard, but you won't get something neat to do unless you team up with some architects. So befriend your architects and befriend them early. This example here is architect Hugh Stubbins and Bill and Measure. I used to work for the company that was founded by Bill and Measure, so I've heard all the war stories and whatnot. Funny thing about him is he never wanted to go into engineering. He wanted to be an architect. So he went to architecture school, he got into it, and goes, I'm not as crazy as my architect buddies, Hugh Stubbins. So I'm just going to go to MIT, get a master's degree in structural engineering, and just work for all my drinking buddies in the architecture school. And it worked out well. But anyway, these 2 guys are going to be the designers for 2 structures. The first one's the Boston Federal Reserve Building. It's tall. It's 500 something feet tall, so many stories, so much base. It's a big cereal box just hanging out in the wind. It won a lot of awards. But let me take a step back. It's on the waterfront. The Boston Federal Reserve controls the money supply in some ways for Boston, New England area. The architect got so many awards. He used this whole innovative space down here. This is the plaza, a couple stories up. All the columns stop. People can walk here, eat their sandwiches, whatever. Down here, people can, just marvel the fact they look up. There's a building above them, but there's no columns. What a great thing. What a great architecture. Good for them. But let's get our head around why the building is the way it is. Since we don't have special weeks, let's just beat it to death with the ASCE analysis method and see what's happening. By using Michael Jackson. Get our head around it. All same with criminal assumptions. We're going to find each one of these things right. Force, it's the wind that's right on the Atlantic Ocean. It's going to want to push this thing over. So find it quick. 580 feet times whatever the height is will give you an area. We're not going to worry about that there's an opening here, an opening there. We can beat the hell out of it later. But just, that's the area. I'm just going to say the wind pressure is 25 pounds a square foot. I'm not going to spend the time to do the curve and say there's 18 and 25 and 41. Professor Letchford could teach you all about wind engineering. But just for this one, 25 pounds a square foot on the building. Gives you a rough idea of how much force is pushing in it. 3 million pounds, get it something a little more useful, 1,400 tons. That's a lot. So that's up there. How the heck is the building not staying open? Same as the Michael Jackson, it's the same as the garage. You have two T's reaching up somehow to grab on. And you can run through the same exercise. Split up that force into two, let each side share the load, 720 tons. The base is 85 feet. Halfway up the building is 290. We're getting a quick handle of what's actually happening. We know the force times the length equals the base moment, 209 ton-feet. Divided by 85 gives you the pushing and pulling value. There's 2,500 tons happening at the four corners of the building. 2,500 tons is a lot of freaking force. It's not such a big deal if you're going to shove it in the ground, 2,500 tons, because the ground's, you can push against the ground. Lifting up against the ground is, it's very hard to do, especially from the Boston waterfront. The whole thing is just this clay mess. There's nothing to really anchor down to. See, they want to make a building this tall. They only have a site that can be so wide. How do you handle this? So assume you can't hold on 2,500 tons, what do you do? Can you screw around with the force? Not really, because the building is what it is. The wind's going to blow what it's going to do. You can't really screw around with the force. You change the length to make the building smaller. It defeats the purpose of having a tall building. You just try to make it smaller. You change the D. Again, not really. It is what it is. So you got to find some way to negate that 2,500 tons of uplift that's happening on Michael Jackson's heels. But we're engineers, and we know that there are several simple things happening at the same time. Maybe we can make use of one of those other simple things. So this is another conceptual lead. It's my old car. Things weigh stuff. There's a dead load in the building, it weighs something. You find some way to make that help you out. The answer is yes, but this is giving away the answer in some ways. What do you have to do to weigh the thing down? What if you pull a number out of your head? What if you pull out 5,000 tons of weight? Can you get 5,000 tons of weight somehow over here? If I weighed 5,000 tons, I have 2 feet. 2,500 tons would go to each foot. I get a similar thing like I did before with the brace frame, where one side adds in, so now I have 5,000 tons pushing on the ground. It's no big deal. The ground's good. You push down on the ground. And the other side does the tug of war, which negates itself. And now you have no uplift. Magical. How do you get 5,000 tons over here? Do you even have it? Well, how much is the building weigh? Again, you're trying to rough out the design of the building over 1 cup of coffee. People work on, and sketch on napkins. This is what they're doing. They're not going, oh, let's talk over some drinks here. Now let me pull up my laptop and run a model for 4 hours and then give you the answer. This is all attempt to give you the brace framework to be able to do it in 20 minutes. How much is the building? 30 stories tall. Let's take a random floor out of it. Take a guess of how much each floor weighs. So what do you do? Take the area. Take a guess at how much it weighs. I'm going to throw out it's about 75 pounds a square foot. Concrete deck weighs about 50. There's stuff hanging. You add up all the things. There's a facade on the side. It's about 75, give or take. You'll refine it later. Each floor weighs a little over 1 million pounds. Each floor therefore weighs about 360 tons. I'm going to put the little arrow up on the top. So there's 630 juicy tons of force up there. It's 30-something stories, but some of it's airspace and whatnot. I'd say there's 28 floors, 28 little baby arrows. They all add up to one big arrow, 17,000 tons. Well, hooray, we got 17,000 tons. There's a problem. How much is the building really worth? We're very confident in ourselves saying you're 17,000 tons here. But your knowledge of the building codes do have to come into play. Because the building codes, like, well, you're so confident you're 17,000 tons, that's great. But I don't want the building teetering over because you happen to think there's going to be more ceiling tiles than there really was. So there's low cases in the building code you have to follow. And the one that we care about only allows you to use 60% of the weight you think is there to resist the wind. That's the one for anybody who's familiar. So you take 17,000 tons, kill 40% of it, all you really have is about 10,000 tons to actually work with. I'm going through this exercise only because you need 5,000 tons on each side. The whole building, all in, weighs 10,000 tons. You need to get every juicy little dead weight you can to get over here to resist this thing. Now the magical purpose of the great architectural lobby starts to become an effect. Here's a shot of the structure during construction. You've got brace frames on both sides. These are the Michael Jacksons keeping the building from falling over. You take a shot of each floor space. People walk around, they never see any cross bracing. It's all handled on the sides. You take the weight from each floor. It's a beam's job to get the load of the columns. Every floor has 630 tons. The columns' job are to collect them, send them on down. In a normal building, you want to get it to the ground as quick as you can. So in a normal building, these columns go all the way down to the ground and get to a foundation. But in our case, we need, desperately, to take that juicy dead load and get them over here to resist this uplift force to keep our building from falling over. So we need that force to end up over there. It's conceptually necessary to put something over here. I wish I had a picture of the truss. I don't. So you're going to have to make do with this kind of ghetto truss-shaped thing here. So imagine put a 2-story truss. All the columns are coming down. He's got truss going in and out of the page, and big trusses that are very, very expensive because it's carrying 30 stories of building, 200 feet. But he needs to do that to get the dead load over the sides to resist the uplift forces, which I thought were going to appear here. Oh, and by the way, if you wanted to design the truss really quick, you could put 2 cantilevers back to back, treat it like a beam, you can get the pushing pulley forces of the top cord, bottom cord really quick. Just trying to show, you get that in your head, no structure can't happen. So hooray. The building is shaped the way it is because of what, here's the reason we just talked about. Keep that in your head. You can conceptually make any building veto freedom real quick. Guys became famous because of it. They kept doing taller and taller buildings, became better and better. And they took that same kind of conceptual thought process to their next building, and it always screwed them. Citicorp said this famous conversation about engineering ethics and what happens when a building is an imminent threat to the public. More on that. The building is twice as tall. It's in downtown Manhattan. The thing that's neat about it, people called it something's whistle. Whoever at Citicorp put the building, like, oh, that's Frank's whistle. It looks frankly stupid. I think it looks stupid. Citicorp buys up a whole city block of New York City, but the one person that won't sell is a church. Why should God move for Citicorp? They say, we'll sell you our air rights above us, but we want a new church, and we don't want your business going through our church. We want to see the sunlight coming in on Sunday. We don't want any of your columns anywhere near our church. Okay, we're not going to. Sounds good. Thank you for the air rights. So what they ended up doing was moving, instead of having this thing on 4 stilts in the corner, they moved that one in. And I got talking and talking, like, why don't we just put all 4 of the columns stilts in the middle? It looks neat, it's great. We use a similar methodology we did over at the Boston Federal Reserve Building. We designed it, sounds good. The idea is it's tall, it catches the wind. But I kind of gave it away. It was almost a no, bad, sad face.
This building could have killed tens of thousands of people.
In 1977, Citicorp Bank built the 7th tallest skyscraper in the world. It was a symbol of corporate confidence in a New York on the brink of financial collapse. The safety of the structure, like any tall building in Manhattan, was taken for granted by the thousands of people who crowded into the area. What they didn't know then was that the tower had a major design flaw.
The first time I heard the story, I knew it was a good story because it began with a dramatic scene in the Citicorp boardroom when a structural engineer came in to tell them that this spanking new beautiful tower had a flaw in it. And not only that, it had a flaw so bad that it could wipe out 18 blocks of Manhattan if a high wind came along.
In the worst case scenario, this was not a building that was going to just simply crumble and fall down. This was a building that was going to tip over and win. And it would cause domino. It would cause the next high-rise and the next high-rise to fail. And how far that would go? Probably the most extreme that I heard was that it could go as far as Central Park.
It's a really, really good story. In fact, there's not time to go through all the twists and turns of it. We'll hit the high points of it. The one thing that was, imagine the building was built the year you were born. It would guaranteed to falling over by the time we're talking now. It wasn't some like vague, oh maybe if a hurricane hits it when a missile hits at the same time or something crazy. A wind was going to come along once every 15, 16 years and it would just blow it over. So there was a problem. If you don't know the story, I'd encourage you to remember this. Take a physical and or mental picture of this. Google 59 story prices. It's a whole article. YouTube that. Hour video. It's great. If you want to really know every twist and turns of why the geometry is such that made the building so damn unsafe, you can take a picture of that and you remember it for all time. We can find some way to email us. But we're here, so let's hit the high points. We don't need to wonder why the building is unsafe. We have the ASCE analysis method with criminal behavior. You find your T. So we're going to do the same kind of thing. We're going to assume that we're going to find the middle of the building. We're going to spread the bottom of the T as wide as we can. column to column. Let's see. Imagine forces, find pushes and pulleys, see where we go. I didn't mention earlier on, anybody who's taking statics or equilibrium knows, there's a force pushing here. There's always going to be a force pushing against here, down here as well. We haven't been talking about it. It's going to come to play into this one. Another simple thing to keep in mind. We'll find our force, find our length, find our D, find our pushes and pulleys, eventually. This is a floor plan. Pick a floor, any floor. No columns around here. It's all office space. People have their cubicle farms, elevators, bathrooms in the middle. Very few and far between columns, but the key thing is there's going to be big mammoth jamma columns in the middle, which line up well. Big mammoth jamma columns. When the wind pushes on a floor, your D is your width of your foot. You go as far as you can with the things that are going to resist the force. That's your D. Then you find your pushes and pulleys. It just works out great. The measuring stuff is the same thing they did there. There's going to be a huge uplift force that's going to be hard to resist. We got to weight it down somehow. What do? We take the dead load that's on the floor. We shove as much of it as we can out to the outside. Some has to come to the inside too. Those beams spanning like that. And then you find a way to collect as much of that dead load that's living out here to shove it into where your P's are. It's a real kind of Looney Tunes way, but real slick way of designing the outside of your building. You take the dead load that's lurking at every one of your floors. You collect them up in these, they're not just braces, they're actually columns, but instead of going down, they're out there. And you collect the load toward the middle, collect the load to the middle, collect the load to the middle, and so on. So you end up getting this one giant dead load force pushing down right where you need it to resist the uplift force. Same thing as Boston, but kind of crazier, but it's the same idea. It works great. These braces do kind of double duty. When this building is getting pushed down, there's this tension load holding your heels down, and there's this tension load that's kind of all along your back or this side of the building. So these braces all go into tension too. But you work the numbers out, you design the connections, and you work it out slickly so the dead load that's coming down the brace is about the same load that's in tension on it due to wind load. It works out clever. Or slick, these are all adjectives. Meanwhile, this side's worrying about the tension load, the other side of the building is worrying about the compression load. These side walls are free to worry about whatever shear forces are happening here to resist that. Works out great. This shouldn't be an extra key. So the story goes, a student calls him up. The building gets built, and there's a professor at a school in New Jersey somewhere. Princeton. Those New Jersey schools? And this professor's saying, whoever designed this thing's an idiot. You put the columns in the corners, because that's what you do for buildings. And somebody was assigned to study this building. So the student, whose name was lost to history, but now we figured, I don't remember her name, but it's now known. She called up Mr. Ledger saying, no, my professor says you're an idiot. I'm supposed to study your building. He has a bit of an ego, and he goes, look, I'm going to give you all my design notes. You're going to know exactly why we did everything. Tell your professor to shove it. The building's designed great. She goes away for a couple of weeks, calls him back. Hey, professor, this is, Mr. Ledger, this is a slick way. I'm all for it when the wind blows at a 45 like this. And I see that you have your loads figured out all nice down here. You've got to design a connection here for 200 tons, and this one's for 150 tons. I see what you're doing there, but if the wind blows in at a 45-degree angle, instead of just hitting the broad side of the barn, doesn't that screw you up? Aren't all your loads way off? And it hits on them. They spent 3 years designing the building, doing all the detailed analysis and all the things people go to school for. But again, they just missed that conceptual leap way early on. What's the wind loaded at 45? The building codes didn't force you to check it back in the day. They do now. So he didn't do anything wrong, really. He just put Michael Jackson the wrong way. When the wind's blowing at 45, all four columns are going to kind of whack and shack to resist it. And whereas your D used to be the full length of the building, really your D that you have to work with is some fraction less of it. We're all experts in Michael Jackson now. If your D goes down, what happens to your P? It goes up 40%. Crap. So now I've got 40% more tension load that I had to worry about originally. Yeah, it's getting shared per two columns, but now these shear forces, which I've been kind of ignoring up to this point, they whip around the building in kind of a weird way. At the end of the story, all my wind forces, crap, the student's right. I'm about 40% off on all my wind forces. Building's built, people in it. I got paid a lot of money to design it. I built a career and I feed my family to this. What do you do? So it's a great, great story. And at first he thought he was going to be fine. It's like, these things come out in little pieces. Now, but I know every connection is fully penetrated weld. If I have this much steel, I put this much weld on it, which is stronger. So I know the weld won't break. A week or so later, maybe I'm forgetting the order, he's in a meeting with the same steel company to do a similar building somewhere else. And they go, hey Bill, we're gonna do the same thing we did in the City Corp building, right? We're gonna bolt all those connections. We're gonna weld all the connections. Well, no, we bolted it. What do you mean you bolted it? Well, your team down in New York, we were talked about it. You know, bolting, well, who cares? The bolts are perfectly designed. Don't worry for all the forces you had on your drums. They're fine. But the forces are out by 40%. Oh, crap. So it turns into this great story. If you watch the YouTube video, it's half an hour long, interviews and whatnot. He goes up to the woods. He's like, or first he talks to his wind tunnel test buddies in Canada. Like, what kind of wind are we talking about? Are we talking about like once every 200 years? You know, can I die first before the building falls over? What's this going to happen less? And they work it out. They figure, well, again, sometime in the next 16 years, the building's going to snap about halfway off and just kind of fall over like this. Here you go. So he goes up to his cabin in Maine. He talks it over with his colleagues. One night he goes, well, I'm so effed. It's so bad. I have no choice but just to tell people, I'll lose my job, I'll lose whatever. It's horrible. So he goes and tells Hugh Stubbin, hey Hugh, buddy old pal, I completely screwed up your building. Great, talk to the lawyers. They go down to City Corp and they fess it up to City Corp. Building's hopelessly screwed up. I've got a plan to fix it. By the way, it's like summertime and hurricane season's coming up. If a hurricane comes into New York, your building will fall over. So they get the Red Cross involved, but the Red Cross doesn't want to tell people why. They're taking these random surveys. I know how many people are in this building, how many people are in this church. Why? I was just curious. It's all lost. It's all lost history. It's a great story stemming from just a little conceptual leap, screwed up in the first 10 minutes, turned into a whole thing. This is getting near the end of the story.
The wonderful thing, you see, when we were designing the building with Hugh Stubbins, having a big ego myself, I loved my diagrams for these diagonal members. I would be very pleased to have them show on the surface of the building. But Hugh Stubbins put the kibosh on that from the beginning. No, no, no. This was a blessing to me, because these joints were all therefore accessible. And the actual mobilization to get at them and fix them was relatively straightforward.
The work was to be done at night and as secretly as possible, as soon as the office started.
All we had to do was strip off gypsum board fireproofing and we could see these joints. The actual fix putting pieces on both sides of the steel diagonals across the joint which was held together with bolts. And within a day or two, the first connection started being put in place.
So it goes on. So the whole kind of purpose of the presentation was to try to put in your mind that one simple shape that doesn't matter if you're in engineering school, if you're anything, if you can keep that in mind, it's the same how your arm moves, the same how a telephone pole moves, blah, blah, blah. Any structure you can pretty much sum up in that one shape. And that's one simple thing that you'll have to keep in your mind. When I was in school, I was so damn bad at remembering everything. I would study for a test, I would forget it 2 weeks later, and I would just move on to the next thing. Collecting my B's, collecting my A's, or B's. And I realized when I graduated, I had no way to retain the information in my mind. So I came out, I got a degree, I was almost worthless. I just forgot everything. So what is a structural engineer? It's a structural, I'll give a quick analogy. You ever see a chess player, hear of a chess player play 30 games at the same time? Oh, he must have such a fantastic memory. Studies showed that the chess player doesn't have any better memory than anybody else. If you randomize the pieces to a way that the game would never unfold, he can't remember anything. But he has a framework to know, oh, this is this kind of move, and this is this kind of development. He sees the patterns in the framework, and that's the way he becomes an expert chess player. For any discipline you go to, it's going to be something similar. I don't have it, but I'm sure somebody who's got 30 years of structural engineering experience has a framework in their mind, locked in there somehow, how to view the whole discipline. They can remember 50 buildings at the same time because this is a steel frame building in an urban area, high seismic, that means something. Here's a 1970s building, I'm going to put a story on the top of it. It's a concrete building, that means something. It spent 30 years to develop it, to have this framework. You scale back to me, kind of lurking around 10 years experience, I kind of have a framework that I'm trying to use to remember things, because memory's so bad. Back that all the way up to after 4 years of RPI, you should be able to have some sort of framework in your mind to remember it, otherwise you're going to forget it. So this was an attempt at one point of me trying to remember how everything I learned at RPI that was relevant to structures got stored in my brain somehow. Every person's going to have a different one, and it's kind of crazy. You see crazy people drawing these on YouTube. The moral of the story is, lurking in here is the only measured time and distance, the only 3 kinds of forces, a spring, mass acceleration, one other things. That smooth criminal analysis method is lurking here. A force times these lines or distances equals a moment. You go through strength of materials only to figure out how to get your pushes and pulleys. All your equations, all your calculus are lurking somewhere in here. And the program is very good about presenting all these things to you. Your strengths, or IEA when I was here, called that something different. Just beat the heck out of everything that's statically determined. You just play it on this side of the sandbox. Shear and moment diagrams, shear and moment diagrams. Dynamics, it's the same damn thing, but you just have things moving around. So you have 2 more other kinds of forces. At some point, knowing how, what is it, deformation over a distance is rotation, hopefully I'm not saying this backwards. You know what a deformation is, you know what a rotation is, you know what a curvature is. At some point, strength of materials connects it all together somehow. Calculus just lets you use differential calculus to kind of march down, string the integral back up. All these things are presented in some way. You can be cute with the way you think about this to have stiffness methods and flexibility methods, throw in more stuff. At the end of it, your capstone class, the assumption is, since you've learned all these things 15 weeks upon, it's all in your mind somewhere. But it's never in anybody's mind. It just usually isn't, because you just forget. It's natural. But the assumption is when you come out that you're crackerjack on it. So try to, as you're, if engineering is the art of having one long continuous thought, that means you have to do the thinking, which everybody's good at, the communicating, which people are okay at, and the remembering, which everybody's bad at. I'm just trying to say, try to have some mechanism so you can retain stuff over time, over years, notebooks, Gmail, whatever you do. Because you get into a problem saying, well, I learned it one time, but I don't really remember it. It just, that doesn't do you any good. You can never get up to building the skyscrapers. All else fails. Don't forget this. And just realize that all your statics in IEA is basically just doing forces over distance equals a moment. Moment diagrams, over and over again. Your strength of materials takes it from here, there's some moment, and you assume it's over a 2-foot wood beam or a 4-foot steel column or whatever. That S section modulus is just a clever way of finding your D and so on and so forth. Analysis method to daisy chain all these things together in the frames and beams, design, put it on a drawing and sell it for a couple $1,000 bucks. And if all else fails, just go to Michael Jackson. We'll let you do it. That's the presentation.